Okay, I'm just going to do a little video on what centripetal force is. And we're going to do this with just a little real world example. So, say we're here and we're just and we're holding onto a string with a stone or something on the end, and we're just swinging it around and around. Okay, well, I'm going to look at this stone for a second. And we're going to see here, and its velocity vector, well, if you remember, they're always tangential to the circle, so they're always just touching it at one point. And you can actually you can check that this is true. Like a lot of people, if they're swinging a stone around, they think that when they let go of it, maybe the stone will travel in this direction and start spinning in, but it won't. It'll go straight in a straight line, because if it wanted to come in, well, there would have to be some force pulling it. If it's going to turn, there's going to have to be a force, and if we've let go of this rope, there's nothing pulling it in anymore, so it's going to go in a straight line, and you can tell. So it's actually just going to keep going out in that direction, okay, because there's nothing anymore, so there'll be no curl or spin in it or anything like that. As soon as you let go, it's going to go in a straight line. If I let go here, it would go in a straight line out there, or if I let go here, it would be a straight line. There won't be any of this, because if it had to have a turn, its velocity would have to change, and that would have to have a force, but there's no more force on it from the moment you let go of the rope. So let's look at this a little bit closer. So if we have now a couple of milliseconds later and we're swinging this around, and now our stone is here, and again our velocity vector is tangential to the curve, okay, we can see that if from here our velocity vector is going in this direction, and then a couple of milliseconds later it's going in this direction, and well, that means our velocity has changed, so we have to have an acceleration. Okay, the speed mightn't have changed, but its velocity has changed because there's an acceleration. And if we say, well, this is a stone, so that means we have a mass and it's accelerating, well, then we have to have a force, don't we? And this force is what centripetal force is. Okay, so this is the force that's providing this acceleration, that's turning it. And now a lot of people, when you swing this around, you might feel like that the stone is pulling that way and that the stone wants to go that way. But it doesn't, and if it did, you would know when you let go, because then really it should go this way, shouldn't it? There's no way turning that way. As soon as you let go, it's going to go straight. And the force is actually being pulled in. Okay, the force is being pushed in, and this may seem a little strange because you feel like it's pulling out, but the force is actually coming in, and it makes more sense if we think of maybe in a car. So if you're in a car, and all of a sudden the car accelerates in this direction, well, what do you feel? Well, you don't feel it. You feel like you're getting pushed back, don't you? And this is the same sort of thing. Okay, so you could think that you're going the other way, but you're actually going forward. The force is pushing you that direction, but you feel like it's the other way. So that's sort of the explanation of what that is. Now, so if we look, we have this force coming in, and we have an acceleration. So you'll see it in your log tables. Now, you don't need to know, but they say acceleration for this. The centripetal acceleration is what this is. Well, this is given as v squared over r. Now, I could derive this, but it's a little bit more complicated than you'll need to know anyway, and you can just look at it. It'll just be in your log tables under circular motion. And so what we can then say is our centripetal force is just going to be equal to the mass multiplied by this acceleration, which is going to be v squared over r. And you'll find that again in your log table, so you won't need to remember this or anything. And that's saying that the force being pulled in has to do with the radius, so how far it goes out, which makes sense, doesn't it? Because it's going to be changing velocities slowly or quicker depending on how far it is out here. In here it's going to be much quicker than the velocity that it's moving, and the mass at the end. Okay, but we can do a little bit more than this. So if we look at A is equal to v squared over r, when we're dealing with circular motion, we love to have things in our omega. Do you remember our angular velocity? And we can do this. So if we remember one of our equations, well, we had, let's get over here. So we had v is equal to omega r. didn't we? So the linear velocity, or the speed that this is traveling at, the velocity it's traveling at, is our angular velocity, and the radius, the distance from the center. And so we can do more to this. So if we square both sides, now you don't need to know this derivation, then we're going to have v squared is equal to omega squared or squared. And then we can insert this in here and get a different value. So now our acceleration could also equal to, instead of v squared, we have omega squared or squared, and still over or. So we can look, that'll cancel, and that'll cancel with that one, and we're left with a is equal to omega squared or omega squared, depending which way they do. So now we have two other ways for our centripetal force. We have this equation up here in terms of the linear velocity, and we have it in terms of our angular velocity. So our other equation then, let's stick it maybe down here, so our other force equation can be given as m omega squared or. So we have two different equations that we can use for centripetal force. One is with the angular velocity and one is with the linear velocity.